Hey, everyone! So glad you're here. I know your Unit 2 exam is right around the corner, so I've whipped up this super special last-minute power-up session. We're going to make sure you walk into that test feeling totally confident and ready to crush it. Okay, are you ready for your study power-up? Let's go. We are going to speed run through the 6 most important concepts that I am almost positive are going to show up on your exam. Think of this as your secret weapon for your final study push. Ready? Let's do this. First up, let's talk about the absolute foundation of all parallel programming, decomposition. This is all about how you take one ginormous problem and chop it up into cute little pieces so that all our processors can work on it at the same time. Okay, for real, you have to know this one. This is one of those questions that's just always there. You need to know the difference between domain and functional decomposition like you know your own name. So let's put them side by side and figure it out. This table is basically your cheat sheet for this topic, so listen close. With domain decomposition, you're splitting up the data. So imagine you have a huge, beautiful picture. You just give each processor its own little square of the picture to work on. They're all running the exact same program, just on different data, which is why we call it SPMD, single program, multiple data. Now, functional is the total opposite. You're splitting up the work. The classic example is a factory assembly line, right? Each processor has a different job, a different function, and the data just flows from one to the next. That's why we call it MPMD, or multiple program, multiple data. So what's the big takeaway here? The absolute key thing to tattoo on your brain is this. If you have a massive amount of data, domain decomposition is your best friend forever, because you can just keep throwing more processors at it. But with functional, you get stuck. You can't have more processors and you have different jobs to do. That is a huge difference, and you've got to know it for the exam. On to our second topic. So we've decided how to split the problem up, but now we have to ask, just how big should those little pieces be? This is called granularity, and trust me, it can make or break your program's performance. And this table shows you exactly why. Fine-grained decomposition is when you make tons and tons of tiny little tasks. It seems great at first, right? You get lots of parallel work, and it's super easy to balance the load. You just hand out a little task to whoever's free. But here's the catch, and it's a big one. The communication to computation ratio is awful. The processors spend more time talking about the work than actually doing the work. Coarse-grained is the opposite. You have just a few really big tasks. This totally slashes that communication problem, but it makes it way harder to keep all your processors busy. And this right here is the golden rule. If you remember one thing about granularity, make it this. Every single time a processor sends a message, it has to pay this little time penalty called latency. If you have thousands of tiny, fine-grained tasks, you're paying that penalty over and over and over again. But by bundling the work into big, coarse-grained tasks, you only pay that penalty a few times, making your whole program way, way more efficient. Ooh, okay, lean in for this one. This is a total pro tip for a classic exam question. Matrix multiplication shows up all the time. And if you know the best way to parallelize it, you are going to look like a genius and score some serious points. So pay attention. Boom! The answer you're looking for is 2D block decomposition, or as it's sometimes called, a checkerboard pattern. Don't just split the matrix into rows or columns. That's 1D, and it's not very good. Instead, you split it into a grid of 2D squares, just like a checkerboard, and you give each little square to a different processor. This is the secret to keeping communication low. And here is your 6-point checklist for a perfect answer. Number 1, using 2D blocks maximizes data locality. Number 2, you use the owner computes rule, which just means whoever owns a block has to calculate its final value. 3 and 4 are about being efficient. You group your communications together and even overlap them with computation so the processor is always busy. And finally, number 5, you make the block size bigger for more coarse-grained tasks. And number 6, you map your processor grid to the real physical network. Do all that and you've got max performance. Let's move on to something that feels like actual magic in our parallel programming toolkit, the prefix sum. You might also see it called a scan operation. It seems so simple, but it unlocks so much power, it's kind of crazy. So what is this magical thing? A prefix sum just takes an array of numbers and makes a brand new one. In the new array, each spot holds the sum of all the numbers that came before it in the original array, including itself. Simple, right? Let's just look at this super easy example. Our input is 1, 2, 2, 1. Okay, so the first output element is just 1. The second one is 1 plus 2, so that's 3. The third one is 1 plus 2 plus 2, which is 5. And the last one is the sum of everything, which is 6. So our final output is 1, 3, 5, 6. See? I told you it was simple. So you might be thinking, okay, that's cute, but why do I care? Oh, you care because it's the secret sauce for all of this. It can help parallelize loops that depend on each other. It can clean up arrays super fast. It can hand out resources without anybody fighting. It's even a core part of fancy sorting and load balancing stuff. It's a total multi-tool. All right, you're doing great. Let's talk about how our little processors actually chat with each other. On your exam, you'll probably get a question like this. You need to pass out data at the beginning of a problem, and then you need to collect all the answers at the end. How do you do it? Okay, picture this. Stage 1. The program kicks off, and just one processor, we call it the root, has all the starting info. It needs to send that same info to every single other processor. What's the best way to do that? The answer is a one-to-all broadcast, and here's why. You need to know this. First, it just makes sense, right? You have one message that needs to go to all the nodes. Second, it's crazy efficient. It doesn't send a million separate messages. It uses this cool tree-like pattern that gets the info to everyone in just log base 2 of p steps. It's way, way faster. And third, our networks are literally built to handle this without getting all jammed up. And now for stage 2. All the processors have finished their work and they each have their own little piece of the answer. We need to gather all those pieces at the root and combine them into one big final result. For this job, you need an all-to-one reduction. I mean, the name says it all. It takes data from all the processors and reduces it down to one final value at the root. It's super smart because it combines the results as it goes, using that same tree structure, but backwards. This is so important because it stops the root processor from getting totally swamped with 1,000 messages all at once. No bottlenecks here. Okay, deep breaths, everyone. We have reached the final boss of our Unit 2 review. This is the one that always trips people up, but if you can master this, you'll show you're a true pro. Let's break down the difference between all reduce and all-to-all reduction. Okay, look really closely at this table because the difference is everything. The most important row is final state. With an all reduce, every single processor ends up with the exact same identical copy of the final global sum. It's like doing a reduction and then a broadcast right after. Now, with an all-to-all reduction, everyone ends up with a different piece of the result. Here's the analogy. In an all-reduce, everyone gets the whole pie, the exact same delicious pie. But in an all-to-all reduction, everyone gets their own unique slice of the pie. So here it is, the answer to the million-dollar question. If you have a system with high latency, meaning it takes a long time for messages to travel, the problem isn't the size of the message, it's the number of times you have to send one. An all-to-all reduction can take p-1 steps. If you have 1,024 processors, that's 1,023 separate messages, each paying that awful latency penalty. No! But an all-reduce with its super efficient tree thingy takes only 2 times log base 2 of p steps. For 1,024 processors, that's just 20 steps. 20! It's not even a contest. All-reduce wins, hands down. And that's it. You did it. We covered decomposition, granularity, matrix multiplication, prefix sums, communication patterns, and we even defeated the final reduction boss. You are officially powered up and totally ready for this exam. You've got this. Now, just for fun, next time you're lagging out in your favorite online game when there are 100 players on screen, which one of these concepts do you think is the secret culprit? Something to think about. Good luck on the test. You're going to be amazing.